Thank you so much, Steve. So my talk will be focused on issues relating to urban sustainability and some of the things that we have done in this area. The specific, so the effort I'm talking about is in the area of urban sustainability. This is an effort that has been funded by the National Science Foundation. It's a joint effort between Colorado State University, Arizona State University, University of California, Irvine, and the University of Maryland at Baltimore County. So urban systems, so the other thing I want to emphasize is this is an effort that is focused on the United States. Most of the data that we're dealing with is focused on the United States, in particular urban areas. But our methodology does not preclude us from sort of making this applicable worldwide if need be. But the focus that we are looking at right now is the US. The project is about 18 months old. Most of the US urban population, most of the US population lives in urban areas, about 80% of them. And one of the things about urban areas is that we draw in impact natural resources and ecosystems quite heavily. And we have a vast amount of data that has been made available to us by government agencies. They could be state, federal, and also non-governmental institutions as well. So how can we tap into this wealth of information? So the project hello? So the project that we have is the Sustain project. This is the project website. And I will quickly go over the team, what our goals are, and then I will sort of talk a little bit about some of the operational data sets that we have, what the features that we currently support, and where we are heading towards. So the project PIs at CSU, we have, besides myself, we have Mazdak Arabi, Jay Bright, Sudipto Ghosh, and Sangmi Pallickara. At Arizona State, we have Mikhail Chester. At UC Irvine, we have Amir Aga Kochak. And at UMBC, we have Claire Welty. We have lots of students working on this. Several students, both current and past, have contributed to a huge chunk of this effort. We also have a couple of research scientists that are involved in this effort as well. So what are our project goals? One of our project goals is to federate voluminous data sets, federate data sets available from diverse sources of different natures and sort of work with this. We also need to be able to visualize these data sets, perform these visualizations at scale, and to also have support for model creation, validation, refinement, and sort of design and develop analytical tools that could benefit the wider community. So what are some of our operational data sets? So here we have data set from diverse data sources. These could be US federal agencies like the EPA, the Census Bureau, FEMA, HIFLD. This is where a lot of our infrastructure data sets come in. The US Geological Survey, CDC, NASA, NOAA, and also the European Space Agency. We have data sets from different projects, including ERAMS, climatology labs, FINE-ET, and the synthetic infrastructure projects. We have data sets from NGOs like OpenStreetMaps. And the data formats that we're dealing with are quite diverse. So this could be point data, it could be gridded data, it could be data sketches, it could be shapefiles, they could be images. And all of these data sets can be encoded in over 30 different encoding formats. And we have to reconcile these things and provide support for visualizations, modeling, and analytics over these diverse data sets. That's the crux of this effort that we're dealing with. All right, so we have a wide variety of data sets that we now have support for. Okay, so these includes demographic data. For example, this could be data sets from the Census Bureau or the American Community Survey, and this could include things like it could include things like income. It could include things like what percentage of the household has insurance, health insurance, education levels. It could include things like what are the commute times that people have for going to work, for example. We have data sets about community services like fire stations, hospitals, urgent care facilities, and so forth. Why are these things important? From an urban sustainability perspective, this is important because this tells us which areas are likely underserved or in relation to the population density and so forth. We have infrastructure information, things like power plants, electrical substation, gas pipelines, water distribution infrastructures, locations to dams and locations of dams, how much, how big they are, and so forth. We also have a slew of information relating to different risk indices. They could be things relating to natural hazards, social vulnerability, flood zones, community resilience. All those things are there as well. We have data sets, climate data sets, both historical data sets, current data sets, and if you're looking at the MACA and GridMat data sets, we're also looking at what is likely to happen in the future. And we're looking at things that are going to happen 80 years from now, 70 years from now, 50 years from now. All of these things could be used for planning purposes. We have data sets, remote sensing data sets. These include satellite data sets, MODIS, Sentinel-2, Landsat, Suomi, FIRST. We have data sets that are directly related to well-being, such as the air quality data sets or flood zones. And we also have incorporated support for COVID data sets within Sustain. We also have support for Evapotranspiration, the National Land Cover Databases, and snow drought data sets. All right, so what are our current capabilities? So we can support data explorations across diverse data sets from different domains. We can support geometry and relational queries. This includes range, proximity, intersections across data sets. We also have support for visualization so that you can render phenomena and outcomes, explore phenomena at different levels of granularity, at different spatial and chronological timescales. Graphing capabilities, so given a spatial scope, we want to be able to chart data across different collections, and how can we do it very effectively and in real time. So these are things like histograms, kernel density estimation, scatter plots, line plots, and so forth. We also allow you to fit models to data, fit models along different administrative boundaries. It could be census tracts, it could be counties, it could be state levels, and so forth. And here we are supporting different modeling schemes, like it could be linear regression. For clustering, we have a bunch of different clustering algorithms that we support, or you could use ensemble methods like random forest and gradient boosting to fit your models. What are our ongoing efforts? So currently, we are building support for AI and deep learning models, different classes of models that you can fit models over. Network models, so that you can understand vulnerabilities from a network perspective. Model validation, so that you can parameterize models and then continuously validate them against ground truth, see how well your models are performing, and so forth. And to also support perturbations of these different variables that contribute to vulnerability, and assess how well your system can handle, how resilient your system is to any issues that might arise. So for future directions, we're including support for bring your own models, build your own data, and so that you can bring any model that you want. We will parameterize it for you and execute it within our clouds and render those results for you. You can also bring your data to see how the system can render your phenomena. So one thing I wanted to quickly do is to give you a 1-minute demo for what this looks like. Okay, so this is very easy to use our system. So this is, you go to the Sustain website, and this is our Aperture Tool, and this is our science gateway that allows you to explore phenomena. So here, for example, if I'm looking at identifying regions where, let's say, folks who are sort of on the younger side are living, primarily college students, let's say, what I'll find is that so this is rendering locations. This is rendering locations over here, for example, where if I look at these things, these are primarily university housing. If I specify a different location again, that is, these are areas where students are living. Yeah, these are all areas where we primarily have university housing. Okay, so the other thing over here is if you want to build a model over this data where you want to sort of identify areas of spatial similarity, you can still build models over this. So with that, what I will do is I will stop here, let Sangmi present, and I'll hang around for any questions that you might have.
Thank you very much, Shrideep. So I'd like to talk about another project. This is an ongoing effort that involves large-scale geospatial data modeling and data retrievals, and also, of course, data storage service over this remote sensing data set. As a team, we're sharing the goal of
Sangmi, you're muted.
Sangmi, you're muted.
Efficient water management. Thank you very much. So especially for this agricultural irrigation systems. So to achieve this goal, the understanding water system of the earth is obviously critical. So if you know how much of water your crop needs in addition to this natural precipitation, that would be a great starting point for your irrigation scheduling. So in this point of view, there have been a great body of works on the concept of evapotranspiration. So evapotranspiration is basically, it refers to the amount of water released to the atmosphere from the multiple sources, such as some evaporation from soil and surface and transpiration from vegetation. Though this is a very great idea and concept for this water management and water system, however, measuring the actual evapotranspiration is very costly. Therefore, it has been a great challenge to get evapotranspiration measures at a scale with a high precisions. So these applications rely on this ET estimating model to get these values. So our project Find ET, we're targeting to provide high precision evapotranspiration values for daily decision-making process at the field level farmland. So this work is funded by National Institute of Food and Agriculture. So before I go into more detailed information, let me introduce our team first. So this is a multidisciplinary research involving experts from computer science, irrigation and water science, and statistics and ecology department at Colorado State University. We also work closely with USGS as well. So in the last 10 years, there have been many research about incorporating these values from this remote sensing, especially for the satellites, to this ET estimation models. However, so this satellite images, there are many publicly available satellite images, and they are equipped with a rich set of sensors and radars. However, incorporating these satellite images directly into our project to achieve the goal of roughly daily and field level precisions, such as smaller than 30 meters, that is quite impossible because of this mismatching resolutions in terms of spatial resolution and temporal frequencies. So Landsat or Sentinel systems, they provide sufficient spatial resolutions, but their frequencies are quite sparse. On the other hand, MODIS and VERS, they provide sufficient frequencies of scanning. However, their spatial resolution is still very sparse. So therefore, to address these challenges, we built this workflow of this project. So getting this public data, majorly from satellite systems like MODIS and Landsat, and climatology data. And then this data set is integrated and ingested into our modeling layer. So in this modeling layer, we include some of the newly built models as a part of this project and some existing models as well. By means of using this model layer, we provide a set of functionalities as a part of FineET toolkits to the users. So this toolkit capability includes some advanced features, such as some imputation queries and analytical queries. This workflow is implemented using this distributed data storage and computing clusters, which is completely compatible with cloud computing environment. So as an example of our advanced query, I'd like to introduce our imputation query in this talk. So let's say we have a Sentinel image and MODIS here. These are two mismatching frequencies and that resolutions. So this Sentinel image is delivered every 5 days like this, and MODIS pretty much every day. So using these two mismatching observations, what we're trying to do using this imputation query is we try to generate unavailable data and then provide it to these modelers and at the end to the farmers. So as a result, let me compare this imputation query output versus true output from this Sentinel satellite image here, collected here. So this left-hand side is a target data from actual Sentinel satellite systems. And the right-hand side is the results of our imputation query. Okay, so behind the scene, what's really happening? So we start from this observation of unique characteristics of the satellite images. Unlike most popular images we can get, such as portraits or sceneries, this satellite images has two distinctable features in it. So first thing is row system or topographical components. Like if you saw these things yesterday, highly possibly you will see these things today as well. It's slowly evolving. On the other hand, there's a fast evolving features such as weathers or seasonality related features. To cope with these two different types of features, and we learn how to estimate this non-existing images, we built SatNet, which is a variation of this generative adversarial networks. It's a type of deep learning model. So this generative adversarial networks, it involves two different networks inside, and then we let them compete with each other. So one works on generating synthesized image, and another one is testing how realistic the other one is, that artificial image is. So we are using MODIS image as a kind of clue for this fast evolving features. And we're using a previous Sentinel image to show the slow evolving features within these networks. Now, training this machine learning model is another big challenge because we use 2 to 7 terabytes of satellite images to train our model. So we use TensorFlow from Google as a base framework, and we also use Harvard from Uber as managing this synchronization of these parameters here. So once this SatNet is trained using this satellite images, how do we use it to generate query outputs? So basically, this is one of the examples. So we use these 3 retrospective sentinel images. This like for the day D, which we are looking for this non-existing image. 3 previous images and 1 small, but it gives a good clue for this current weather. The modest image goes into the SatNet and we generate this output here. So the performance of our imputation query was our PSNR value was 3234 and MSE was 0.0009 to 0.0024, the imagery with the cloud coverage of 10%. This PSNR here is that the metrics we usually use to see that how realistic that image is. So when we consider that this commercial grade compression engines, and they target 30 to 50 of PSNR values, then we can see that our imputation query is performing quite well. And in terms of the inference time on GPU, our imputation query takes 10 to 40 milliseconds to generate this synthesized image. So, besides this high resolution remote sensing, synthesizing the imageries to generate this ET values, we are also doing ensembling models to address that model sensitivity issues for this geospatial and temporal variability. And also we are working on this embedding-based ad hoc analytics and the band imputation such as TIR or NIR band, specific band values. So most of the works here are published and these documentations are available in our project webpage. Thank you very much.
Okay, thank you both for interesting applications of the use of big data to analyze certain questions and address certain questions. Now, I'd like to brainstorm with you both on how you would take these applications or how you could see using the data that we hope to produce with the Earth Archive, we are producing in some cases, and use that with your applications or, use it with your applications. Or with your models, with your tools basically that you've produced.
Yeah, so I think I can take one part of it. So I think we have worked with lots of diverse data sources. We are in the process of working with radar data as well. So I think the only data source that we have not worked with is LiDAR. And I think, because we have gone from points, point clouds, data sketches, shape files, images, satellite imagery, they can be hyperspectral at different resolutions, even though it's being captured by the same satellite radars. And so I think what LiDAR can bring to the table is slightly different from a sustainability perspective. And that is, I think if there are, when in the morning, when I was looking at one of the talks, I think it was Voxel Max, but they showed that they were able to identify areas of archaeological importance. That is clearly an area that you should not be developing in. So I think those kinds of detections can be done even better if you're able to combine different data sources. Where to have development, where to not have development, and how can we have leverage these different data fusion methods where you're pulling in data, not just from one source, but from lots of different sources, correlate all these different types of information. And I think in general, Sangmi and I, we do a lot of work in AI and deep learning and machine learning. And I think those can be used to quickly identify points of interest to actual researchers so that their attention can be focused to these specific problems or specific areas. I think that's where I see possibilities where we can deal with that data, that type of data, especially the type that Earth Archive will produce.
I mean, I'd like to address, have you think about the same thing from the specific application that you showed, because watching yours, I could immediately see in my own mind some possibilities. I'd like to hear yours.
Yeah, so there are some, this LiDAR kind of information is such a valuable data set. So from data generation's point of view, we can actually even think about for the area that this LiDAR scan is not ready to publish, we can actually still provide some kind of artificially generated information for the modelers. That is very important, especially in the case that if we integrate some other data like Shrideep mentioned, then even if that is not truly real data set, it will be still very useful. And on the other hand, whenever we think about some LiDAR scanners are going through our overhead, some area here, then probably some people will be worried about privacy issues. And those kind of privacy issues, you can pick and choose some part, you can expose it, some part you can hide it, but still you can maintain very valuable statistical values, like something like you can use, let's say, some differential privacy kind of ideas, you can apply that kind of models as well, so that it is completely artificial, completely random, but still valuable information will be delivered to the modelers.
That last point is very interesting, because in the last presentations before yours, one of the issues that was brought up was areas that indigenous groups might not want released. And yet what you're saying is we could take that information, keep it private, but still extract some statistical information for other users, for example, ecological modelers, as opposed to the cultural heritage side, or people who are looking at carbon sequestration in the areas while keeping hidden the data which is sensitive to indigenous groups.
Exactly.
Very, very interesting. Well, I think we're just about at time. I'd like to thank both of you for your presentation and for showing us a real application of how big data can be used, because that's one of the questions that comes up when we talk about this, is how can we actually use this data, and can we even use it if it's such huge data storage issues, such huge amounts of data. And you're showing this clearly possible in with today's world, doing things on the cloud and other stuff. Thank you very much.
Thank you, Steve.